Okay, welcome to the first lecture in Math 105. So basically what we'll be doing is looking at the learning activity for prerequisite section 1 in this video. I apologize if there's too much background noise. I'm going to try and see about getting a better microphone for these recordings in the future. But in the first section, Module 1 will be covering P1, P2, and P3. So in this lecture, we'll just be going through the P1 part of the worksheet. So if you don't know how to navigate to this guide, it's a PDF available on the Blackboard page. So let me take you through that. So this is what your Blackboard homepage looks like. And underneath the college algebra, you can just scroll down to active modules. So click on modules. Right now, for the first 2 weeks, we have Module 1 available. So click there. And you have a bunch of stuff. You can see the assignments that are due this module. So there's 4 of them, and they'll basically be following that format for every module. There'll be 8 modules total in the course, each one lasting 2 weeks. But what we're going through, just to get the hang of the material, is the learning guide. So if you click this click here icon, it will download as a PDF. And that is what we're looking at now. So we'll basically be going through the first 10 or so problems. Let me see. On each one of these, there's a sorry, just changing the pen to draw. There's a solved problem and a pencil problem. So what you'll want to do is you'll want to try and read through the solved problem on your own and see if you understand it. And if you can follow that, then you want to pause the video and give pencil problem number 1 a try. And once you finish that, you can start the video back up again and make sure you got the same answer that I did. So this first section will kind of be covering basic algebraic manipulation and plugging these things in. So problem number 1, 4 plus 5 times the quantity x minus 7 to the third power for x equals 9. So basically they just want you to plug in 9 for x and make sure that you handle the order of operations correctly. So let's go ahead and do that. Alright, so here we have 4 plus 5, and then we want to replace the sorry about that. We want to replace x with a 9 to the third power. Okay, pretty sensible first step. Now we come to the problem of order of operations. So if you remember the acronym, please excuse my dear Aunt Sally, PEMDAS. Write that up here. So what that generally stands for is you want to do anything in parentheses first, then you want to apply exponents, and then multiplication / division comes next, and then once you've finished any multiplication and division, you want to do addition and subtraction. So in this problem we have something inside parentheses, 9 minus 7. So that's what we want to do first. So we'll do 9 minus 7, which we know is just the quantity 2 to the third power. Now we want to, the next thing in order of operation is exponents. So we want to raise 2 to the third power. So let's see about that. So 2 to the third power is 8, so we have 4 plus 5 times 8. Okay, so now we have an addition and a multiplication, and order of operation says multiplication should come first. So we have 4 plus 40, and now that's all that's left is addition, and we see that our answer is 44. Okay, so let's move on to the next one. So this next problem is a bit of a word problem. Let's see what they're asking us to do. It says the formula P equals 26 times x squared plus 819 times x plus 15,527 models the average cost of tuition and fees T for private U.S. colleges for the school year ending X years after 2000. So that's something important to note right off the bat. So if they want you to evaluate something, say in the year 2005, that means in that formula up there you would plug in 5, not 2005. Whenever it says X years after 2000, you're going to just plug in the difference of that number and 2000. So that's kind of what they're asking us to do here. They say use this formula to project the average cost of tuition and fees at private U.S. colleges for the school year ending in 2013. Okay, so they basically just want us to plug in the number that corresponds to 2013 in this formula. Remember, X is the years after 2000, so we're just going to plug in the number 13, not the number 2013. If you plug in 2013, you're going to get something that's way too big. So let's, sorry, I didn't mean to click that. Okay, so we have our formula and we want to plug in 13. So basically the tuition in the year 2013 is going to be given by 26 times 13 to the second power plus 819 times 13 plus 15,527. Okay, so some of these numbers might get kind of big, so we may want to do them on a calculator. And if you don't have a calculator handy and you're doing these by the computer, what we can do is, again, go back over to the Blackboard page, and if you look on the left hand side, we have a scientific calculator and a graphing calculator that you can just click on, and it will take you to a page where you can do these calculations. So what do we have? 26 times 13 squared. Well, if we come back to that calculator, we can do that here. So 13, this x squared button means square it. Remember to square that number. And then we want to multiply that by, let's see, I forgot already. So let me go back. 26. Okay, so we want to multiply that by 26. We see that number is equal to 4,394. So let's go back over here and write that down. I forgot already. 4,394. Alright. Let's see if we can write that down. 4,394. And then let's see what 819 times 13 is. So let's clear everything. Gosh, I'm forgetting my numbers. 819 times 13. Okay, so 10,647. So let's write that down. So 10,467 plus 15,527, and then we add these numbers together. So hopefully we'll be able to remember them all. I doubt it. 647. So I got that one wrong. Sorry, did I switch the 6 and the 4? Yeah. So let me try and erase that. So 647. It's supposed to be an eraser now. Alright, so let's go back. Sorry, I'm still getting the hang of this new recording software. Alright, and 647. Okay, so let's see if we can try real hard and remember these numbers. Maybe we can just kind of go side by side so we don't have to remember quite so much. Okay, so we have 4,394 plus 10,647 plus 15,527, and that gives us the average tuition of 3,568. So the average cost of tuition and fees at private U.S. colleges is really expensive. Alright, let's go back to the next problem. There we go. Alright, let's see. Okay, so problem number 3. These are a little bit more simple than the last few. You just have to know what they're talking about. So here they're talking about intersection in problem 3 and union in problem 4. So intersection pertains to the concept of sets. And basically what a set is just a list of either a bunch of numbers or things. In this case, we have two sets, so kind of two different lists in pencil problem number 3. The first set contains the numbers 1, 2, 3, and 4, and the second set contains the numbers 2, 4, and 5. What that intersection does, or that little upside down looking U thing between the two sets says, is it wants to combine the two sets into a new set, and the way it does that is intersection means I'm going to write down a new set with all the elements or numbers that are common to both sets. So if a number lives inside both of those two sets, then we say it's in the intersection. Okay, so let's see where. Okay, so we want to make a new set, and we can just write it down, and that's a curly brace. So what are the numbers that are in both sets? Well, the numbers 2 and 4 are common to both sets. Notice 1 and 3 is only in the first set, and 5 is only in the second set. So our intersection here would be 2 and 4, and then we would close the braces. And that is our intersection. Easy enough. Okay, so let's look at the next one. It says find the union. Well, if the intersection means what's common to both, union's kind of like the other end of the spectrum. It wants you to list all the numbers that are in either one set or the other. Doesn't need to be in both sets, it just has to appear one time in either one of the sets. So in some sense the intersection is going to be a smaller set and the union is going to be a much bigger set. And also whenever we're writing down things in terms of sets, we don't have any redundancy. So if you have 2 appearing in both sets and it's in the new set, we don't write it down twice. We still just write it down once. So what is the union going to be here? Well, we want to write down all numbers that appear in one set or the other. So basically, what are all the different numbers that occur? Well, there's 1, 2, 3, 4, and 5. So that will be our union. 1, 2, 3, 4, and 5. And that is the set. Okay. So hopefully you're clear on unions and intersections. Okay, pencil problem number 5 talks about different subsets of the real numbers. So for this sort of thing, basically we want to break down the real numbers into some common subsets you might have heard of. The natural numbers, those just stand for all the numbers you can use for counting. Okay, so examples of counting numbers are 1, 2, 3, 4, 5, any number that you can count to. So what are numbers that are not natural numbers? Well, any negatives, any fractions, any really irrational or funny numbers like pi, things like that. So if we look at our set above, at first it looks like there aren't any natural numbers. Negative 11, we can throw that out because it's a negative, so we can't count to it. 5 over 6 is a fraction, so that one's out too. 0, generally we start our counting numbers at 1, so that's not a counting number either. 0.75 is a decimal, so that doesn't work. On the square roots, if you're not sure, what you can do is you can go back to the calculator over here, and this SQRT means take the square root. So for example, if we do 5 and then take the square root, we see that it's this number over here, 2.23, and this is just an approximation. This number actually keeps going and going and going, but basically the calculator is just going to show a certain number of decimal places, in this case 10, so it stops after 10 decimal places. Okay, pi we also know is a number that's not a whole number, so that one's out. It's 3.1415926, and it keeps going. But the square root is 64, so here's where they're trying to trick you. You might think, oh, all square roots are kind of right funny, they're going to end up decimals, but no, let's be careful to check. If you do 64 and then take the square root, we'll see that it's the whole number 8, which we can clearly count to. So in this case for 5a, to list the natural numbers, what we want to do is we want to just write down the square root of 64, which simplified equals 8. So that would be the natural number from that set. Okay, what are the rational numbers? Well, in this case, the rational numbers, if you don't remember what that is, let's look at the root of the word ratio. What does ratio mean? That means basically a fraction. So any number that can be written as a fraction is a rational number. So there's going to be quite a few in our list there. Is negative 11 a rational number? Sure. Negative 11, we could write that as a fraction by writing it as negative 11 over 1. So negative 11 is certainly a rational number. Negative 5 over 6, also a fraction. That's okay. 0, once again, we could write it as 0 over 1, so that works. 0.75, what could we do with 0.75? Well, say the number out loud. 0.75, if we actually use the way they taught us to say it in grade school, it would be 75 hundredths. So 0.75 really stands for the fraction 75 over 100. So 0.75 is also a rational number. And then we also know the square root of 64 equals 8. So that is, once again, a rational number. Let me go ahead and erase that work we did there so you don't get confused. So this is the list of the rational numbers that are pretty obvious. What about the other two numbers that we didn't write down, the square root of 5 and pi? Well, these two numbers turn out not to be rational numbers, because when you look at the decimal expansion, they never terminate and they never repeat. So these are examples of irrational numbers. Usually if you have a square root, it's not going to be rational unless it ends up terminating or being a nice number. And fancy numbers that have these Greek letters to symbolize them are almost never rational. So note that. Square root of 5 and pi are, what do we say? We say not rational or irrational. Okay, so our list of rational numbers just includes those 5 numbers. Yeah, again over here in the example problem before, they describe the rational numbers. The confusing ones that are decimals are ones that either terminate or repeat. What's an example of a rational number that doesn't terminate but ends up repeating? Well, so here's think about 1/3. 1/3, if you would write that as a decimal, is 0.333333, and it just keeps on repeating. So a lot of times they'll put the bar over the last number that keeps repeating, or the sequence of numbers that repeats. So notice that this is a rational number because you can write it as 1/3. So this is rational, but does not terminate. Okay. Pencil problem number 6. We're dealing with inequalities. So here we want to determine whether it's true or false. So remember, when you have an inequality symbol, something like x less than y, what does this mean cognitively? What's the idea of this symbol? This would say that x is smaller than y. Or y is bigger than x. So when I got taught this in grade school, I think my teacher said you want to imagine this as the alligator's mouth, and the alligator always is really hungry, so he wants to eat more or something, so he opens up toward the bigger number. Okay, so let me go ahead and erase that, and we'll figure out which one of these is true. Okay, I didn't erase. Okay, so we just have to make sure that the number that the alligator's mouth opens toward is actually bigger. So they gave us some negatives, which are a little bit tricky, because although -7's bigger than 2 in terms of negatives, the larger the absolute value, the larger the negative value is actually a smaller number. So -2 is bigger than -7. So this one would be true. Another way to think about it is you can picture all your numbers on a line like this, and then you would think of 0 as being here, maybe you would think of 2 as being here, regular 7 being here, and then the negative numbers are going to be the numbers left of 0. So you might have -2 over here, and -7 would be somewhere all the way over here to the left. And when you look at numbers, if you want to figure out which ones are bigger or which ones are smaller, bigger numbers are always to the right. So is -2 bigger than -7? Well, it's farther to the right on the number line, so it sure is bigger. Again, let's look at this next one and try and draw the number line. Maybe that'll make it very clear. So let's put 0 in the middle. Put 2 over here, and then where would -5 be? It's somewhere over here to the left. So what is this inequality statement saying? It would be saying -5 is bigger than or equal to the number 2. Well, we know that's false. -5 is smaller because it's to the left. So this one would be false. Alright, again, you have some similar problems over here solved for you. Okay, let's continue on this next pencil problem. So they want us to rewrite each expression without absolute value bars. So what that means is we want to evaluate or figure out what the number is. So absolute value just means the distance from 0 on the number line, or basically you can evaluate inside like it's parentheses and just change the sign to the positive value. Either way is going to be equivalent. So here we basically know that pi is the number that's about 3.14, so we know that this is positive, and if it's positive, absolute value doesn't do anything to it. So this is actually just equal to 12 minus pi. If you want to put the numbers together, you'll get an approximation. It won't be exactly equal to, but that might be the safer way to do it. So you could come back to the calculator and just do 12. Let me clear everything first. So let's do 12 minus 3.14 just for an approximation, and you get about 8.86. So yeah, so if you wanted to do it that way, you could also write 12 minus pi is approximately, I use squiggly equal sign to mean it's about, not exactly equal to, would be the absolute value of 8.86. And then since that's a positive number, we don't need the absolute value bars, so that's just 8.86. And that would be about the value of 12 minus pi when you do the absolute value. How about the next one? The square root of 2 minus 5. Well, we know that that is going to be a negative value, so we want to switch it to the positive value. So let's try it with the approximation method first. So let's go back to our calculator and do the square root of 2. So you hit 2 square root, and then we want to subtract 5. So minus 5, and hit equals. So we get that that number is negative 3.59, let's say. So let's go back and see how we might write this down in terms of actual approximation. Okay, so if we want to do the approximation, this would be approximately equal to absolute value of 1.41 minus 5. And that's going to be equal to negative 3.59. And then what does absolute value do? It says, well, we just want to take the positive version of that value. So you have positive 3.59. Another way to think about it, if you don't want to approximate, is what did it really do? It just flipped the numbers around. So we just changed the sign on the whole expression. So another way to do it is we could write the absolute value of the square root of 2 minus 5 is really just equal to the opposite value of that expression, the square root of 2 minus 5. And that is in fact equal to, we could distribute the negative sign across the parentheses and end up with negative square root of 2 plus 5. So most people will probably prefer just to use the approximations and end up with positive 3.59. But I just want to show you that it's possible, once you realize which number is bigger than the other, to keep the exact form of the expression. Okay. 7c is actually not that tricky. What are we doing? Well, we have negative 3 over the absolute value of negative 3. So the top just stays the same, and applying the absolute value just makes the negative 3 on the bottom positive. So we get negative 3 over positive 3, which just gives negative 1. So that would be our answer. Okay. Absolute values, like I said, if you don't want to think about them as turning positive numbers into negatives, they also have the interpretation that they can be used to denote distance on the number line. Okay, so let me make this a little bit bigger. Okay, so our pencil problem tells us to find the distance between negative 19 and negative 4 on the real number line. So you can think of this probably pictorially, or you could actually go ahead and use the absolute value to figure it out. So let's think about the number line. So let's draw a big line, and negative 19 is some big negative number way over here on the left. Then you've got negative 4 over here, and then all the way up here is somewhere like 0. So we're looking for what is this distance between these two numbers. And you can see it's the same distance you would have between 4 and 19 on the other side. So you can just kind of pictorially tell that they are 15 apart. That's kind of just using the method of looking at the picture and using common sense. But how could you figure it out otherwise? Well, we could just write down their difference in terms of the absolute value. So the distance between any two numbers we'll just call them x and y is, you can always figure that out by just doing the absolute value of x minus y. And the order doesn't actually matter because the absolute value is always going to give you the positive value. So let's do that down here. Let's look at, let's just do negative 19 minus negative 4. Those are our two numbers. Remember, whenever you have two negatives, those turn into a positive value. So we end up with the absolute value of negative 19 plus 4, which is going to give us the absolute value of negative 15, which is positive 15, which is exactly what we thought we would get by the common sense approach. So that's two different ways to do the problem. The absolute value way is a little bit more abstract, but once you've thought about what it means in terms of the number line, you can really see that there's a clear connection between the picture and the formula. So anytime you have two numbers and you want to figure out how far apart they are, you can just do the absolute value of their distance. Okay. So objective number 9 really talks about I know what I did. Just asks you to identify a couple names of properties. So there's a few. The commutative property they illustrate here, which means if you add two things in two different orders, you end up with the same number. The second one, so 2 plus the square root of 5 is going to be the same as the square root of 5 plus 2. And then, 9b just says, okay, anything you multiply by 1 gives you the same number back. I think we all know that. It's really not too important to know the names of these properties, but you want to know how they work. So 9a, pencil problem number 9, this is what's called the associative property of addition. So that means if you have three things added together, no matter how you group them, you're going to end up with the same thing. Let's look at the left-hand side. We'd work inside the parentheses first, so 2 plus 7 would be 9. 9 plus 6 would give us 15 on the left side of the equation. How about on the right side? Well, the parentheses make us add 6 and 2 first now. So we get 8 plus 7, but again, that's still 15. So that means no matter how we group the numbers, we end up with the same answer. So this is what's called the associative property. Of addition. If you would want to write it more generally, you could say something like x plus y plus z always equals, I don't want that grouping symbol there. Let me erase that. So I wanted to write down it's really equal to x, and then group y and z. Okay, how about the next one? So this is a really important property. So what happened here on the left side and right side? We could check by adding inside the parentheses and using order of operations. So we know that negative 8 plus 6 is negative 2. Negative 2 times 2 is negative 4. On the right, we see that negative 16 plus 12 equals negative 4 also. So both expressions are equivalent. But how did you get to one from the other? Well, what happened here was they took 2 times negative 8 plus 6, and we multiplied across. So we did 2 times negative 8, and then we did 2 times 6. And that gave us 2 times negative 8 equals negative 16, and 2 times 6 equals 12. So this is what's called the distributive property. And we have this kind of property whenever we have multiplication interacting with a addition or subtraction problem inside the parentheses. So the way you would do something like this in general is you would do, let's see, let me erase that to give a little more room. So this would be, if you have, say, A times B plus C, what happens is we multiply the A and the B. So we do A times B, and then we add that to A times C. So the A gets distributed across the parentheses. We multiply it times the B, and we also multiply it times the C, and then we add the two together. Okay, so 10, I think this is, this is the last one for section P1, so they want us to simplify. We're going to have to use some of those properties, and basically whenever you have a bunch of grouping symbols like this, they're really checking to make sure you know how to distribute, and also that you're doing your order of operations. So I always start with the innermost set of parentheses, the ones that are kind of nested the furthest. So in this case we have two sets. We have the bracket parentheses, and then inside those parentheses are the regular rounded parentheses. So what do we do first? Well, we can't add 4y and minus 5. They don't go together. They'd have to look alike. So as simple as those can be is the way they are right now. So we do have the parentheses, and what's keeping us from dropping those parentheses right now is this negative sign. We need to actually distribute the negative sign because the negative sign is being multiplied across the parentheses. So first what we want to do is distribute. So we have 7 minus 4, then let's keep the square parentheses, the brackets. So then we have 3 minus 4y, and then plus 5. And we've gotten rid of that innermost set of parentheses. So notice we took the negative, we multiplied it by 4y to make it negative 4y, and then we also took the negative and we multiplied it by negative 5 to make it positive 5. Okay, inside the parentheses now we can do some work, because 3 is a regular number and so is 5. So we can put those two together. So let's keep the 7. We're not messing around with him yet. The negative 4 can stay. But let's put 3 and 5 together. They're both positive numbers. So they give us 8. And then we have minus 4y still left over. Okay. Now what? Well, we have a negative 4 and a set of parentheses. So it's up to us to use the distributive law again. So we have the 7, negative 4 times negative 8 gives us minus 32. And negative 4 times negative 4y gives us positive 16y. So it's important to remember that we're distributing the whole negative 4. We're not just distributing 4. This negative is attached to that number when we distribute. So one of the most common mistakes you can make here is to forget about that negative sign. Okay, now what's left? Well, 7 and minus 32 can combine. So that gives us negative 25 plus 16y. And we're all done. So, again, you can always come down to the bottom to get the answers for the pencil problems and check our last one. They have it as 16y minus 25. We have minus 25 plus 16y. But by the commutative property, those two numbers are really the same. Okay, so that is it for the prerequisite section number 1. And I'll be coming to you with some videos for P2 and P3 in the near future, hopefully on a better microphone. Thanks. Bye.